Work and energy. Exercises. Q1. Write detailed answers. Explain the difference between potential energy and kinetic energy. Answer. Kinetic energy and potential energy are the two forms of energy which any object or body have. They are different from each other in following ways. Q1. B. Write detailed answers. Derive the formula for the kinetic energy of an object of mass m, moving with velocity versus. Answer. Let us say an object of mass m is moving with speed v, so energy which the object has because of its motion or speed is its kinetic energy. Now, let us assume object was initially at rest. Some work was done on it to increase its speed to v and it gained kinetic energy. Now from law of conservation of energy, we know kinetic energy will be equal to work done on the object. Suppose F force was applied on an body of mass m, initially at rest to increase its speed to v in time t. In this time object also covered distance s. We know work done W on a body of mass m, which moved a distance s due a force F applied on it is given as W equals F times s. Also, force applied on the object of mass m moving with acceleration a is given as F equals ma. So, work done will be W equals ma times s. We have Newton's second equation of motion which related displacement s covered by object in time t, having initial velocity u, with its acceleration a. Equation is initially object is at rest so, initial velocity is u equals 0 meters per second so, equation becomes. So, putting value of displacement s, we get work done as. This can be further simplified as using Newton's first equation of motion which relates final velocity versus gained by object in time t, moving initially with initial velocity u, with acceleration of the object as v equals u plus at. Initially object is at rest so, initial velocity is u equals 0 meters per second. So, equation becomes v equals 0 plus at equals at now, replacing the value of v in above equation to find the work done we get. Now this work done is equal to kinetic energy of the object of mass m moving with velocity v, i.e. kinetic energy of the object is Q1. C. Write detailed answers. Prove that the kinetic energy of a freely falling object on reaching the ground is nothing but the transformation of its initial potential energy. Answer. Let us assume an object of mass m is kept at rest initially at a height h above the ground, and object is suddenly released, so it will gain speed, and let the velocity of object just before hitting the ground be v. The situation has been shown in figure. Initially object of mass m was at a height h above the ground so potential energy of the object is P equals mgh is acceleration due to gravity. Now when object approaches ground, just before hitting the ground let the velocity of object be v, so its kinetic energy will be. Now, applying Newton's third equation of motion for motion of object version 2u2 equals 2 atto Siemens. Here versus is final velocity of object, u is the initial velocity of the object. S is the displacement covered by object and a is its acceleration during motion. Now initially object was at rest, so its initial velocity u equals 0 meters per second. The object is coming downwards due to gravitational force applied by Earth, so its acceleration is g, i.e. acceleration due to gravity i.e. a equals g. Due to acceleration final velocity of object changed to v, in moving from height h to ground, so its displacement is s equals h. And putting the values in the equation we get v2o2 equals 2gh. Or we get value of square of final velocity is version 2 equals 2gh. Now, putting the value of v2 in equation of final kinetic energy of the object we get. Solving we get final kinetic energy of the object as Ke equals mgh. Initial potential energy of the object is Pe equals mgh. Now we can see final kinetic energy of the object is same as the initial potential energy of the object. And since initially object was at rest, so its initial kinetic energy was 0, and finally object was just near the ground, i.e. its height from surface of Earth is 0, so its final potential energy is also 0. This conveys that all the kinetic energy of a freely falling object on reaching the ground is nothing but the transformation of its initial potential energy. Q1. B. Write detailed answers. Determine the amount of work done when an object is displaced at an angle of 300 with respect to the direction of the applied force. Answer. Suppose an object is displaced from its original position due to application of a force which is not in the direction of force. Force is making an angle of 300 with the direction of displacement. Situation has been shown in figure. Now we know work done on an object due to a force is given by relation W equals Fs cos theta, where W is the work done due to force F in displacing object by S, theta is the angle between force and displacement. Here let the force applied be F, and displacement be S, angle between force and displacement is theta equals 300. So, work done will be W equals Fs cos 300. From trigonometry we know value of cos 300 as. So, putting the value we get work done as. So, amount of work done when an object is displaced at an angle of 300 with respect to the direction of the applied force is. Where F is magnitude of applied force and S is the displacement of the object. Q1e. Write detailed answers. If an object has zero momentum, does it have kinetic energy? Explain your answer. Answer. If an object has zero momentum then its kinetic energy is also zero, i.e. it does not have kinetic energy. We know momentum of an object is given as P equals mv, where P is the momentum of object of mass m moving with speed v. Now, P equals 0 i.e. mv equals 0, i.e. mv equals 0. So, either mass of object is 0, or its velocity is 0, i.e. it is at rest. Now object will have some mass, let it be m, so its velocity is 0, v equals 0. Now kinetic energy of any object is given as, where m is the mass of the object moving with velocity v. Putting v equals 0 in the above equation we get kinetic energy as. So, we get kinetic energy of the object is 0j, so it does not have kinetic energy if momentum of the object is 0. Q1. F. Write detailed answers. Why is the work done on an object moving with uniform circular motion 0? Answer. In uniform circular motion work done on an object is 0, because force acting on the object is always perpendicular to its velocity and displacement. In uniform circular motion, the speed of the object is same throughout but the velocity is changing because the direction of motion of object is continuously changing. The object is accelerating, and acceleration is towards the center of circular path in which object is moving due force is also acting towards the center of the circular path, i.e. perpendicular to the direction of motion. The path of circular motion of the object, direction of its velocity, displacement, acceleration and force at any instant has been shown in the figure. As we can see, direction of velocity and displacement at any instant is along the tangent of circle and is perpendicular to direction of acceleration and force, i.e. angle between force and displacement at any instant is 900. Now we know work done on an object due to a force is given by relation W equals F times S times cos theta, where W is the work done due to force F in displacing object by S, theta is the angle between force and displacement. Here let the force applied be F, and vary d mol displacement at any instant be S, angle between force and displacement is theta equals 900. So, work done will be W equals Fs cos 900. From trigonometry we know value of cos 900 as cos 900 equals 0. So, putting the value we get work done as W equals Fs times 0 equals 0. Work done on an object moving with uniform circular motion is 0. Q2. Choose one or more correct alternatives. For work to be performed, energy must be I transferred from one place to another. E concentrated. E transformed from one type to another. IV destroyed. Answer. Option E, transformed from one type to another. Explanation. For work to be performed, energy must be transformed from one type to another, though total energy remains same during this transformation. Example, if we have to fill an tank overhead at some height with water, we will use electrical energy which will run motor and transfer it into mechanical energy of motor, which will push water towards tank, i.e. work is done in displacing water from one place to another, and this work is further converted to potential energy of water at some height above the ground, so energy transforms from one type to another in order to perform work. Q2V. Choose one or more correct alternatives. Joule is the unit of I. Force E. Work E. Power IV. Energy. Answer. Option E. Work IV. Energy. Explanation. We know work done W on a body, which moved a distance s due a force F applied on it, is given as W equals Fs. SI unit of work done is joules J, so 1 J work is said to be done when 1 N force is applied on a body and moves it by 1 meter, i.e. 1 J equals 1 N times 1 meter. Now work and energy can be interconverted, and as we know, work done on a body against some external force to change position of body is potential energy, and work done to increase the speed of the body is called kinetic energy. Now work and energy can be interconverted, and as we know, work done on a body against some external force to change position of body is potential energy, and work done to increase the speed of the body is called kinetic energy. So energy of a body is equivalent to some type of work done, i.e. work and energy have same unit joule. Unit of force is Newton N, and unit of power is watt W. Q2. C. Choose one or more correct alternatives. Which of the forces involved in dragging a heavy object on a smooth, horizontal surface, have the same magnitude? I. The horizontal applied force E. Gravitational force E. Reaction force in vertical direction IV. Force of friction. Answer. Option E. Gravitational force. Option E. Reaction force in vertical direction. Explanation. When an object is dragged on any surface, it experiences four forces: the horizontal applied force, frictional force in direction opposite to the applied force, gravitational force in vertically downward direction due to Earth's gravity, and reaction force due to surface in vertically upward direction. All the forces have been shown in figure. Gravitational force and reaction due to surface are cancelling each other as there is no displacement in vertical direction, i.e. forces are balanced in vertical direction, so their magnitude should be same and direction should be opposite, as is the case. Frictional force should be less than applied force for the box to move or start motion. Q2D. Choose one or more correct alternatives. Power is a measure of the ellipsis dot I. The rapidity with which work is done. E. Amount of energy required to perform the work. E. The slowness with which work is performed. IV. Length of time. Answer. Option I. The rapidity with which work is done. Option E. The slowness with which work is performed. Explanation. Power is defined as the rate of doing work, or it is the work done per unit time. Mathematically, power is given as P equals with T. Here, P is the power when W amount of work is done in time T. So it tells how fast or slow work is being done. Q2E. Choose one or more correct alternatives. While dragging or lifting an object, negative work is done by I. The applied force E. Gravitational force E. Frictional force IV. Reaction force. Answer. Option E. Gravitational force, and E. Frictional force. Explanation. Work done by a force on an object is negative when direction of force acting on object and displacement of object are in exactly opposite direction. Our direction of displacement makes 1800 with direction of applied force, because we know work done on an object due to a force is given by relation W equals F times S times cos theta, where W is the work done due to force F in displacing object by S. Theta is the angle between force and displacement. Angle between force and displacement is theta equals 1800. So, work done will be W equals F times S times cos 1800. From trigonometry we know, cos 1800 equals -1. So putting the value we get work done as W equals Fs, i.e. work done is negative when direction of displacement and applied force are opposite. Now when an object is lifted from ground, gravitational force due to Earth in acting in downward direction and displacement is in upward direction due to applied force as shown in figure. Since gravitational force and direction of displacement are in opposite direction, work done by gravitational force is negative. Now when an object is dragged, frictional force is trying to oppose the motion and hence acts in direction of applied force and displacement. As shown in figure, as displacement of object and applied frictional force are in opposite direction, work done by frictional force is negative. Q3a. Rewrite the following sentences using proper alternative. The potential energy of your body is least when you are I. Sitting on a chair, E. Sitting on the ground, E. Sleeping on the ground, IV. Standing on the ground. Answer. Option E. Sleeping on the ground. Explanation. Potential energy of any object depends upon its height from the surface of Earth. We know the relation for potential energy of an object of mass m due to Earth's gravity. G is acceleration due to gravity, held at an height h above ground is Pe equals mgh. So more is the height of body from ground, more is the potential energy, and less is the height of body from ground, less is the potential energy. Now in case of human body, height of body from ground is measured from center of mass of the body, which is the point where all mass of the body is assumed to be concentrated, the position of which is near the stomach in human body. So potential energy of body will be least in case of a person sleeping, because in that situation height of center of mass of the body will be minimum from ground. Q3b. Rewrite the following sentences using proper alternative. The total energy of an object falling freely towards the ground. I. Decreases, E. Remains unchanged, E. Increases, IV. Increases in the beginning and then decreases. Answer. Option E. Remains unchanged. Explanation. Total energy of a body is sum of kinetic energy and potential energy. Kinetic energy depends upon velocity of body. Potential energy depends upon position of body, height from surface of Earth, and gravitational potential energy. They keep varying, but their sum, i.e. total energy, always remains constant. Potential energy and kinetic energy keeps on interconverting into each other, but the total energy is conserved or unchanged as in accordance with law of conservation of energy. So in case of a freely falling body, speed of body keeps on increasing, i.e. kinetic energy is increasing, but height of body from ground is decreasing, i.e. its potential energy keeps on decreasing. Increase in kinetic energy is equal to decrease in potential energy, i.e. the net sum, total energy of the object remains same. Q3c. Rewrite the following sentences using proper alternative. If we increase the velocity of a car moving on a flat surface to 4 times its original speed, its potential energy I will be twice its original energy. E will not change. E will be 4 times its original energy. IV will be 16 times its original energy. Answer. Option E. Will not change. Explanation. Potential energy of an object does not depend upon its speed, but rather it depends on height of object of Earth's surface, its mass and acceleration due to gravity G, which are constant, i.e. does not change during motion of a car on a smooth road, as we know the relation for potential energy of an object of mass m due to Earth's gravity G is acceleration due to gravity, held at an height h above ground is Pe equals mgh, i.e. more is the height of body from ground, more is the potential energy, and less is the height of body from ground, less is the potential energy. Now here height of car from ground is constant, so potential energy is also same or will not change. Q3b. Rewrite the following sentences using proper alternative. The work done on an object does not depend on I. Displacement, E. Applied force, E. Initial velocity of the object, IV. The angle between force and displacement. Answer. Option E. Initial velocity of the object. Explanation. We know work done on an object due to a force is given by relation W equals Fs cos theta, where W is the work done due to force F in displacing object by S in the direction of force, theta is the angle between force and displacement. Now we can see here work done is independent of initial velocity of the object, so if a body is moving with any velocity or even if is at rest if same amount of displacement is caused with same amount of applied force, same amount of work will be done. Q4a Study the following activity and answer the questions. 1. Take two aluminium channels of different lengths. 2. Place the lower ends of the channels on the floor and hold their upper ends at the same height. 3. Now take two balls of the same size and weight and release them from the top end of the channels. They will roll down and cover the same distance. Questions. At the moment of releasing the balls, which energy do the balls have? Answer. Now suppose two aluminium channels of different height are placed and inclined on a floor such that top of both is that same height, as shown in the figure. Now initially both balls are at rest so they do not have any kinetic energy, and both are at some height above the floor, i.e. Earth's surface, so they will have gravitational potential energy as we know the relation for potential energy of an object of mass m due to Earth's gravity g is acceleration due to gravity held at an height h above ground is Pe equals mgh. Q4. C. Study the following activity and answer the questions. 1. Take two aluminium channels of different lengths. 2. Place the lower ends of the channels on the floor and hold their upper ends at the same height. 3. Now take two balls of the same size and weight and release them from the top end of the channels. They will roll down and cover the same distance. Why do the balls cover the same distance on rolling down? Answer. Now since balls have same initial potential energy as both are at same height above the ground, and all the potential energy is converted into kinetic energy in both the balls, so kinetic energy of both the balls on just reaching the floor will be same. Now kinetic energy depends upon velocity of the ball, since kinetic energy of both the balls is same, so both will have same velocity on the floor, with which they are moving forward. Now both ball will stop after covering some distance due to friction, but since their initial velocity on floor is same they will cover equal distances before stopping. Q4d Study the following activity and answer the questions. 1. Take two aluminium channels of different lengths. 2. Place the lower ends of the channels on the floor and hold their upper ends at the same height. 3. Now take two balls of the same size and weight and release them from the top end of the channels. They will roll down and cover the same distance. What is the form of the eventual total energy of the balls? Answer. Total energy of the ball is sum of kinetic energy and potential energy. Kinetic energy depends upon velocity of body. Potential energy depends upon position of ball, height from surface of Earth, and gravitational potential energy. They keep varying but their sum, i.e. total energy, always remains constant. Now eventually initially ball was at rest at a height h above the surface of Earth, so form of energy was potential energy. Now as we know the relation for potential energy of an object of mass m due to Earth's gravity g is acceleration due to gravity held at an height h above ground is Pe equals mgh. Q4. E. Study the following activity and answer the questions. 1. Take two aluminium channels of different lengths. 2. Place the lower ends of the channels on the floor and hold their upper ends at the same height. 3. Now take two balls of the same size and weight and release them from the top end of the channels. They will roll down and cover the same distance. Which law related to energy does the above activity demonstrate? Explain. Answer. I. The above experiment law explains law of conservation of energy, which states, energy can neither be created nor destroyed. It can be converted from one form into another. E. Thus, the total amount of energy in the universe remains constant. E. As we can see here, potential energy of both the ball have transferred into kinetic energy, and also, kinetic energy of both the balls upon reaching ground was same since their speed was same as they traveled equal distances. This indicates in both cases the initial potential energy, same for both as both were at same height, have been converted to kinetic energy and amount of total energy is same for both the balls, and energy has been interconverted from potential to kinetic in both the cases by same amount, i.e. it can be generalized that total energy remained constant throughout. Q5a solve the following examples. An electric pump has 2 kilowatts power. How much water will the pump lift every minute to a height of 10 meters? Answer. Note, here, electric pump will consume electrical energy, convert it to mechanical energy which will do work on water in raising its height and increasing potential energy of water, i.e. finally all energy is converted to potential energy of water. Power of the pump is 2 kilowatts, i.e. 2000 W of electrical energy is being consumed every second by motor. We have to find water lifted each minute, i.e. energy consumed by motor in 1 minute will be equal to potential energy gained by water in raising to a height of 10 meters. We know energy consumed is given as E equals P times T, where E is the energy consumed by pump in J, P is the power of pump in watt, W, T is the time for which pump is operated in seconds, S. Here power of the pump is P equals 2000 W. We want to obtain energy consumed in 1 minute, so time is T equals 1 minute equals 60 S, so the energy consumed is E equals 2000 W times 60 S equals 120,000 J. Now this much energy will be transferred as potential energy of some amount of water. We know the relation for potential energy of an object of mass m due to Earth's gravity, g is acceleration due to gravity, held at an height h above ground is P equals mgh. Value of acceleration due to gravity, g equals 9.8 meters, s2. Suppose mass of water transferred is m. Height to which water is transferred is h equals 10 meters, so potential energy of transferred water is P equals m times 9.8 meters per square second times 10 meters equals 98 meters J. Now equating potential energy of water of mass m equal to energy supplied by pump. P equals E 98 meters equals 120000. Solving we get mass of water transferred as m equals 120,098 of a kilogram equals 1224.489 kilograms, i.e. around 1224.5 kilograms of water is being lifted to height of 10 meters by the pump. Q5. Solve the following examples. If a 1200 W electric iron is used daily for 30 minutes, how much total electricity is consumed in the month of April? Answer. Unit or kilowatt-hour kWh is commercial unit of energy, measured mainly in case of electrical appliances. If an appliance of 1 kilowatt or 1000 W, spending 1000 J of energy per second, is operated for 1 hour, then 1 kilowatt-hour of energy or 1 unit of energy is used. So energy consumed in unit is given as E equals P times T, where E is the energy consumed by appliance, P is the power of appliance in kilowatt kW, T is the time for which appliance is operated in hours. Here power of the appliance is P equals 1200 W. Converting it to kW, 1 kilowatt equals 1000 W, i.e. 1 W equals 1/1000th of a kilowatt, so power is P equals 1200 times 1/1000th of a kilowatt equals 1.2 kilowatts. Time for which appliance is used daily is 30 minutes. 1 hour equals 60 minutes, i.e. 1 min equals 1/60th hour, i.e. appliance is used daily for 30 times 1/60th hour equals 0.5 hour. Appliance is used daily in month of April, i.e. for 30 days. So time for which appliance is used as T equals 0.5 hour times 30 equals 15 hours, putting value of P and T in equation to find energy consumed. E equals 1.2 kilowatts times 15 hours equals 18 kilowatt hours, i.e. 18 kilowatt hours or 18 unit of energy in form of electricity has been used in month of April. Q5. C. Solve the following examples. If the energy of a ball falling from a height of 10 meters is reduced by 40%, how high will it rebound? Answer. When a ball is kept at some height it gains potential energy, which is its total energy, and when it is released just before hitting the ground all its potential energy is converted to kinetic energy. Now when it collides with ground if no loss of energy is there, kinetic energy of ball remains same as of before collision but direction of velocity is reversed. Now ball goes upward and its magnitude of velocity keeps on decreasing due to gravitational force in downward direction, and finally ball stops attaining original height, where again all the kinetic energy is converted to potential energy, but if energy is lost during collision, the initial speed with which ball starts moving upward is reduced as kinetic energy is reduced and ball attains less height than before. Ball is initially at a height, h equals 10 meters above the ground. After collision let the height of ball above the ground be x. Situation has been shown in the figure. Let the mass of ball be m. Now we know the relation for potential energy of an object of mass m due to Earth's gravity, g is acceleration due to gravity, held at an height h above ground is P equals mgh. Let initial potential energy of object be pi, so putting value of h we get initial potential object of ball as pi equals mg times 10 meters equals 10 milligrams. Now all the potential energy is converted to kinetic energy, so kinetic energy of ball just before collision is K equals 10 milligrams. After collision kinetic energy or total energy is reduced by 40%, i.e. the kinetic energy just after collision Kf is 60% of the initial energy, i.e. Kf equals 60/100ths times 10 milligrams equals 6 milligrams. Now ball will move up with this kinetic energy up to a height x till all its kinetic energy is converted to potential energy and comes to rest momentarily before again falling downwards. Now final potential energy of the ball at a height x above the ground will be Pf equals mgx. Now, equating final potential energy equal to the kinetic energy of the ball just after collision, i.e. Pf equals Kf, i.e. mgx equals 6 milligrams. Solving we get x equals 6 meters. So the ball rebounds up to a height of 6 meters above the ground. Q5. B. Solve the following examples. The velocity of a car increased from 54 km per hour to 72 km per hour. How much is the work done if the mass of the car is 1,500 kilograms? Answer. Now here velocity of a car is increased, i.e. car is accelerated, which means some force is applied on the car, and since car is in motion and accelerating, so it also traveled some displacement from original position. Situation has been depicted in the figure. Now we know force on a body is given as F equals ma, where F force is applied on a body of mass m. To move it with acceleration, we know work done on an object due to a force is given by relation W equals Fs, where W is the work done due to force F in displacing object by S in the direction of force. So putting the value of force in above equation we get the magnitude of work done as W equals Fs equals mass. Mass of car is given m equals 1,500 kilograms. Now, finding the value of as. We know Newton's third equation of motion, which is version 2u2 equals 2 atto Siemens. Here versus is final velocity of object, u is the initial velocity of the object, s is the displacement covered by object, and a is its acceleration during motion. Here velocities are given in kilometer per hour. Converting them to SI i.e. meter per second, we know 1 kilometer equals 1000 m, 1 hour equals 60 minutes, 1 minute equals 60 seconds. So, 1 hour equals 60 times 60 equals 3600 seconds. So we get 1 kilometer per hour equals 1000 m, 3600 s equals 1036 equals 5/18 of a meter per second. Now here initial velocity of the car is u equals 54 kilometers per hour equals 54 times 5/18 equals 15 meter per second. Final velocity of the car is v equals 72 kilometers per hour equals 72 times 5/18 equals 20 meters per second. Putting values of v and u in above equation we get 20 milliseconds minus 1, 2, 15 milliseconds minus 1, 2 equals 2 times as i.e. So putting the value of mass of car and value of as in equation of work done, we get work done as W equals mass equals 1,500 kilograms times 87.5 meters 2 equals 131,250 J. So the amount of work done is 131,250 J. Q5. E. Solve the following examples. Ravi applied a force of 10 N and moved a book 30 centimeters in the direction of the force. How much was the work done by Ravi? Answer. Here a book is displaced by 30 centimeters due to 10 N force, as depicted in the figure. We know work done on an object due to a force is given by relation W equals Fs, where W is the work done due to force F in displacing object by S in the direction of force. Here the force applied is F equals 10 N. The displacement of book in the direction of force S equals 30 centimeters. All units should be in SI, so converting cm to m 1 centimeter equals 1/100th of a meter. So we get displacement as S equals 30 times 1/100th equals 30/100ths of a meter equals 0.3 meters. So work done on the book is W equals 10 N times 0.3 meters equals 3 NIE. Ravi did 3J work to move the book. Q6. Study the various instances of transformation of energy you see around you and discuss them in class. Answer. Now everything around us is working on energy and transforming it from one form to another. For e.g. an electric kettle consumes electrical energy from current and convert it into heat energy, which heats contents inside it. An electric cell has ions of different metals inside it, having certain chemical energy which is converted to electrical energy. When we use the cell and suppose we put it any toy or watch, then that energy is converted to mechanical energy of the toy or watch, and various examples of transformation of energy can be found in the surroundings.